Can you explain why, for a simple pendulum, the natural frequency and therefore the oscillation periods do not depend on the mass, but only on the lever arm from the mass to the pivot points? In this video, we derive the equation of motion of the simple pendulum and show how the natural angular frequency can be obtained from it. In many cases, you will see the coordinates x and y. However, forget about them. We use the simple coordinate phi, which is the rotation angle about the pivot point A. We do this because we then have 1 degree of freedom instead of 2. With this single degree of freedom, we set up a moment equilibrium where we sum all moments with respect to phi about point A and set them equal to 0. This is called a dynamic equilibrium, and this is exactly what we do now. First, we draw the free body diagram and includes all moments that act with respect to phi. Let's start with the gravitational force. This force acts downwards and creates a downward-directed weight force at the mass points, proportional to the mass at the gravitational acceleration. Therefore, Fg is equal to m times g. Since we're dealing with rotation, we need the moments resulting from this force. So we draw a positive moment mg, which represents the moment caused by the gravitational force. Torque is force times lever arm, so we write mg is equal to Fg times h. However, at this point, the difficulty arises with the sign, plus or minus. We will look at this in a moment. First, let's determine what the lever arm actually is. The lever arm depends on the angle because sine of phi is equal to h to L. This leads to h is equal to L times the sine of phi. Now, if we imagine that the pendulum is deflected in the positive phi direction, we obtain a positive h. But the downward directed gravitational force then produces a negative moment for a positive phi, meaning it acts opposite to the defined positive moment direction. Therefore, the sign is negative and we obtain mg is equal to minus Fg times h. Furthermore, we have another moment, which is the inertial moment according to Newton's second law. This is mj is equal to minus j times phi double dot. The minus sign appears because if we accelerate the pendulum in the positive phi direction, the inertial moment acts in the negative direction, that is, opposite to the direction of acceleration. With this, we can now set up the moment equilibrium. We sum all moment contributions and set them equal to 0. Minus j times phi double dot minus mgl times the sine of phi is equal to 0. Now we multiply the equation by minus 1, so that we obtain a positive fleeting sign. Linearize for small angles and therefore approximate sine of phi is more or less phi, and this gives us the equation of motion for small angles phi. J phi double dot plus mgl phi is equal to 0. This is the equation of motion for small oscillations. If you want to learn more about the step-by-step modeling of dynamic systems applied on interesting real-world applications, check out the first link in the description. To obtain the natural angular frequency, we now look at the coefficients in front of the acceleration term and in front of the displacement term phi. The coefficient in front of the acceleration term is the effective mass m tilde, and the coefficient in front of phi is the effective stiffness k tilde. This stiffness represents the restoring effect that stores potential energy, namely m times g times L. If we now consider the moment of inertia of the mathematical pendulum, we have J about the point A is equal to m times L squared. And using the formula for the natural angular frequency, omega 0 is equal to square root of the effective stiffness divided by the effective mass, we obtain after cancellation omega 0 is equal to square root of g divided by L. This shows that the natural angular frequency of the mathematical pendulum is independent of the mass m. If we now visualize this and double the mass once and then double the length L, we see that only the length L influences the natural frequency of the simple pendulum. Changing the mass does not change omega 0. This result is, of course, valid only for the mathematical pendulum, where the entire mass is concentrated at the endpoints.